Hello everyone, I'm Tingyi Gou from University of Science and Technology of China. It's my pleasure here to introduce our recent work about the origin and dynamic evolution of solar eruptive flux loop. I will mainly introduce you a Flare-CME event focused on the Flare-CME coupling during the unusual two-phase evolution. Many thanks to my collaborators from University of Graz, University of Zagreb, other institutes from Russia, UK, and the US. We know that CMEs are large-scale magnetized plasmas that escape from the sun. It usually undergoes three phases of dynamic evolution. First, a slow rise in the no-solar corona, then fast acceleration, finally a propagation phase at nearly constant speeds in the interplanetary phase. Previous studies have shown a temporal relationship between the CME dynamics and the associated flare, and found that the CME acceleration occurs during the flare impulsive phase. More studies have revealed a synchronization between the flare head X-ray emission and the CME acceleration based on the positive feedback between the reconnection and CME acceleration. According to the standard flare model, magnetic reconnection occurs in the wake of the eruption CME, which can release a lot of magnetic energy to accelerate particles that emit at X-ray rays. And it can also drive CME acceleration by reducing the tension of the overlying loops and by providing additional magnetic flux to the CME. And on the other hand, the CME acceleration can also drive faster inflow into the reconnection region, thus to enhance the reconnection rate. So the flare energy release and CME acceleration are closely coupled. But here I introduce you a flare CME coupling different from the standard scenario. It's a solar eruption from the east limb on 2013, May the 13th. It produces a fast halo CME and an intense X-class flare. This CME experiences an unusual two-phase acceleration associated with two episodes energy release in the flare. And this event shows a nice feature of erupting magnetic flux loop as observed in SDO-AIA angstrom images. And the formation of the flux loop structure is also very interesting. We observed it grows from a small-scale state structure and is initiated from coalescence of multiple plasmoids in the cartridge. I'm not going to talk about the details here, and if you are interested, you can refer to our paper published in 2019. Here I'll mainly focus on the dynamic evolution of the CME. This CME is observed by 3 satellites from different points of view, stereo A, stereo B, and also SOHO Glasgow. We use GCS model to fit the CME structure and get its high time evolution in 3 dimensions. We combine the CME evolution in the inner and outer corona observed by AIA and also by GCS modeling. So we can get the complete CME kinematics in the solar corona. We use the high time data and derive the velocity and the acceleration profiles of the CME, as shown by the green curves here, with errors in light green shadows. From the acceleration profile, we can see that the CME undergoes two distinct phases of acceleration. The first is an impulsive peak with a very high accelerations up to 5 kilometers per second square. And second is an extended phase with accelerations of about several hundreds meters per second square. It is smaller than the first phase, but still much higher than many other CME events in the statistical studies. Let's see if CME is finally accelerated to a very high speed, larger than 2,000 kilometers per second, and the acceleration ends at a large coronal altitude, about 6 solar radii respect to the solar center. It also extends largely into the flare decay phase. We also find that the two-phase CME acceleration is nicely associated with two-episode energy release in the associated flare. The first stage shows us the flux-slope eruption observed in steel AIA, similar to the standard Flare-CME event. The second step shows us the reconnection of a large-scale loop lag in the aftermath of the eruption, which sweeps into the reconnection site as a reconnection inflow, and simultaneous outflow is also observed in AIA hot hotspots. We also observe strong hot X-ray bursts at the same time. Also, RESI shows high energy emissions even up to gamma ray range. Evidences very intense energy release by the reconnection. We also find significant injections and increases of type 3 radio emission observed by stereo waves. It finally merged into a large branch of interplanetary type 3 burst. And this increase and injections of type radio emission coincide with the hot X-ray bursts observed by RESI. It evidences both downward and upward moving electrons that are accelerated by the reconnection. If we compare the CME kinematic profile with the flare X-ray flux, we can find a good temporal association between the two-phase CME acceleration and flare energy release. Also between the resultant CME speed and flare soft X-ray flux. It suggests that the second step reconnection not only results in stronger energy release in the flare, but also contributes to the CME acceleration. In addition, we observe clear signatures of ongoing reconnection during the flare decay phase, lasts more than 4 hours. Including continuous growth of the post-flare loop system, downflows of superarcuate loops, and also lower altitude loop shrinkage. This occurs throughout the long-duration decay phase. We also observed significant hot X-ray bursts beyond the flare impulsive phase, even up to 100 to 300 keV, indicates very efficient particle acceleration even during the flare decay phase. And these hot X-ray bursts are nicely associated with the second CME acceleration period. It means that the ongoing reconnection beyond the flare rise phase is still coupled to the CME acceleration up to a coronal height of more than 6 solar radii. In summary, we study the dynamic evolution of a solar eruption. The CME experiences an unusual two-phase acceleration associated with two-episode energy release of the flare. But from the figure, we can see that the impulsive CME acceleration occurs in the first phase, but the flare shows much stronger energy release during the second phase. This is quite different from the standard scenario, in which these two phenomena are supposed to be synchronized. In this event, we observed in the AIA images that the second step reconnection still occurs low in the corona, just above the post-flare loops. So it's capable of accelerating a large number of electrons to produce strong hot X-ray emissions, even stronger than the first phase. But for the CME, it already runs higher in the corona. The Lorentz force accounting for its acceleration becomes much weaker due to rapid decrease of the corona magnetic field. And also the CME has a larger inertia as its mass increasing. So the CME's acceleration is smaller during the second phase as it's running away. Thus, here we observe the impulsive CME acceleration precedes the intense flare energy release. This unusual two-phase evolution finally produces a very fast CME and an intense long-duration flare, and it suggests a close coupling between them throughout two phases, but with different energy distributions. And that's all of my talk. Thank you very much.